So this time I'm going to talk about structured prediction. And this is very important in natural language processing tasks because maybe most of the tasks we're interested in doing are structured prediction tasks. And one of the prediction problems that I've been talking about all this time, where we take I hate this movie, I love this movie, and predict very bad or very good. This is one type of prediction task we can make. And this is one example, but we can also kind of split our prediction tasks into a bunch of different classes, I guess. So we can classify our classifiers, if you will. So we have our two classes, which are our binary classifiers. That might be, I hate this movie, and it goes into positive or negative. We have multiple classes, multi-class. So this is, I hate this movie, and then we get very good to very bad, 5 classes. Or we can have structured classification tasks or structured prediction tasks. Usually we say structured prediction. And these are things where basically we have a very, very large number of labels, so many that we can't handle them properly. And one example of this is I hate this movie, and we get the part of speech string. And the other one is I hate this movie, and we translate it into some other thing here. So how many classes are we classifying over for these two problems? Any ideas? What is the big O of these? Or not big O, actually, we can calculate exactly. So K is the number of tags, and then power length of sentence, yeah. So K to the, let's call it L. Yeah, so for the first case. And what about the second case? Yeah, exactly, it's infinite, because we can generate an infinitely long thing. So needless to say, we can't enumerate all of these, so we can't just do what we would normally do for binary classification or multi-class classification here. So why do we call this structured prediction instead of like exponential class prediction or infinite class prediction or something like that? And basically the reason why is because, so classes are too numerous to enumerate, and we need some sort of method to exploit the problem structure to learn effectively. And here structure doesn't mean anything like parse tree structure or linguistic structure. It just means that there's some like similarity between the things that we can exploit. And one example of this is if we have two part of speech strings, this top part of speech string and the bottom part of speech string are basically very similar. And we can use the fact that we can kind of define the similarity between these two in some way that allows us to do classification or learning in a better way. So I will be talking about sequence. Sorry, go ahead.
Why is it called structured prediction and not structure prediction?
Probably this is just my interpretation, but it's because the prediction problem itself is structured. We might not necessarily be predicting a structure, if you see what I mean. So like normally, at least in linguistics, normally when we say a structure, we're talking about like a tree or something like that. And here it just needs to be some of our choices or some of the things are interrelated in some way. You probably could call it structure prediction if you wanted to, but also another reason why is because in language we have collocations, and structured prediction is one of the collocations that we use fairly often. It's a technical term, so. But I think it does make sense to call it structured prediction because it's the structure of the problem that we're solving, I guess. Any other questions? Okay. So I will be talking about sequence labeling as an example of a structured prediction problem. Actually, as I said, probably if you think about any problem in NLP and it's not text classification, it's going to be a structured prediction problem. So the stuff I talk about here will basically apply to almost everything that you want to do that's interesting in NLP. But sequence labeling is probably the easiest one to handle. So we have one tag for one word, where we could be doing part of speech tagging, where we take in these and predict the part of speech, or named entity recognition, where we take in words and predict tags like this. So people are familiar with this kind of like tagging scheme, maybe, BIO tags. Yeah. So, so this is one way. This is another prediction problem. So as a first attempt to do this, what we can do is we can say each of these tags are independent, and we just want to classify them independently. So in order to do this, what do? We can pad this. We can turn all of these into vectors, and then we can take a window around this part of speech and run it through a neural network and predict the part of speech tag. PRP here. We can do the same thing here, same thing here, same thing here. So we make 4 decisions, basically. Does this work for part of speech tagging or named entity recognition? Has anybody ever tried this before?
There's a paper using independent classifier.
Yeah, there's several papers on that, I think. Yeah. Yeah. Anyway, this is a structured prediction task, in that, or it's a task where we could be able to use structured prediction, but we're not doing structured prediction itself because we're just making a whole bunch of independent choices. Does anybody know how well this works? Or what did the paper say?
It was on like trading structured. This is structured prediction.
Yeah, actually, I didn't add this to the references, but this is a good paper. It's called Trading Structure for Features, where basically they create featureized models. And the answer is this works almost as well as any of the complicated things I'm going to tell you. But it works a little bit less well than the complicated things that I'm going to tell you. So, but you shouldn't laugh at people who are doing something like this, because it actually works quite well a lot of the time, especially for sequence labeling or other simple tasks. Okay, so let's do this with a bidirectional LSTM. We take a bidirectional LSTM and we run over the input sentence, and then we make our predictions here. So is this structured prediction? Anybody? Who says no? Who says yes? So the answer here is no. It's not structured prediction, and the reason why, it's not a structured prediction model, and the reason why is because we are still making independent predictions, even though we have some really fancy feature extractor over the input. Still, essentially, we're taking in a window. We're doing some complicated transformations over it, but it's still a window of words. In this case, it's the window of all the other words in the sentence in making predictions. So this is essentially from in terms of how easy it is to do, it's just as easy as the previous model that I came up with. When it becomes a structured prediction problem is when we start modeling interactions between the output, and then the algorithms basically become hard, I guess. Yeah.
So what's the difference between structured prediction and multitask? Like if we optimize a joint classifier over if we add all the loss functions, then that's just a multitask one, right?
Well, our only task is part of speech tagging, I guess. So it seems like it's a single task to me. But it's multiple decisions. And also, one thing about multitask learning, which I'll talk about more later, is actually those decisions can be independent, and it's still a multitask model. So we might do part of speech tagging and named entity recognition and not model the interaction between the part of speech tags and the named entities. So those would be independent, but it would still be a multitask model. So those are actually different different concepts, I think. Any other questions? Okay, I will move on. So why do we want to do this? This is my favorite example because it gives you a really good example of why structured prediction is important, and it's a famous example that you see everywhere. So time flies like an arrow. We can come up with a number of part of speech tags for this. So this one, this one, this one. Does anyone know what these mean if you interpret them? And what's the first one? What's that? Noun. Oh, sorry. I'm sorry. Not the part of speech tags, but what's the interpretation? Knowing the part of speech tags is important. So the first one is noun. The second one is verb. The third one is preposition and type of preposition, and then a determiner, then a noun. But what I actually meant to ask was each of these rows. What is the interpretation of this row? So the first one is like the common interpretation, right? What about the second one? Yeah, so time flies are fond of arrows. And then the third one, yeah, it's a command form. So please measure the time of flight similarly to how an arrow would, or to how you would do for an arrow. So all of these are interpretations that kind of make sense, but but anyway. So but one of the interesting things here is all of these kind of vary a little bit, right? And if you look at the majority class for any of the part of speech tags and take the maximum frequency, you actually get something totally different. So what this is saying is time flies that are similar to an arrow. It's not even a complete sentence. It's lost its verb. So by seeing this, you can see that there's like lots of consistent part of speech tagging sequences. But if you look one by one and make independent classifications, you actually might get something that isn't consistent, or that isn't one of the things that you expected. So because of this, structured prediction is at least ostensibly important. Okay, so how do we create a structured prediction model? Actually, we've already done something. We've already done a structured prediction model in this class. So what we do is we just take these part of speech tags and we feed them back into our forward, basically our forward encoder here. So by doing this, when you make the next prediction, you will reference the tags that you've already generated. And what is this? This is similar to the encoder-decoder model that we created before. Before, remember, if we had an encoder-decoder, we made one decision, and then we fed that decision back into our network when we made our next decision. So this is how one way we can convert this so it will basically consider the interrelationship between these tags. And if you do that, then maybe if we get to the first one, it will say, okay, I saw a verb first, so I'm very certain that the next one is going to be a noun, as opposed to being another verb. Or I know that I should be including a verb in this sentence somewhere, and I haven't seen one yet, so I should raise the probability of verb next. So, so that gives it the capability to model these relationships. So are there any questions about this? Yeah.
So, I mean, so it's the point that the architecture has to somehow take into consideration that there is a sequence instead of, because the time decisions are not necessarily independent, but they share a lot of features, right? And you're generating context when you move the time.
The tagging decisions themselves are independent. They only depend on the source. If you think about them from a machine learning perspective, what we mean in machine learning by independent is that basically you don't condition any of your other decisions on on each other. So just to write it down in a formula, which maybe I should have done earlier on the slides. But when I say independent, I basically mean our probability of the whole sequence is equal to this. So the only thing that we use when we condition on the only thing we use when we predict the next tag is the input sentence. And from the point of view of the neural network, here we haven't fed in any of our tags into the neural network when we calculate the representations that are used to make the decisions next time. So from that point of view, it is completely independent for this one. For this one here, we make a decision and then feed that back into the neural network before making our next decision. So that's the big difference.
In this one, so why would we prefer say feeding from left to right versus feeding right to left?
That's a good question. There's no reason at all. So you could feed from right to left. The only possible reason is that humans read sentences from left to right, or specifically they speak sentences from a previous time point into the next time point. In English, you read sentences from left to right. In Arabic, you read sentences from right to left. In Japanese, sometimes you read sentences from top to bottom. But if you follow the order that humans are processing the sentences, it might make more sense. That being said, that's an empirical problem for a machine because there's no reason why a machine should do the same thing a human should do. But also empirically, you tend to do a better job when you follow what humans are doing. So you tend to do a better job when you go from left to right than when you go from right to left also. Okay. Any other?
So in that context, I actually remember you telling us on LSTM
Yeah.
that left to right is to work better on language modeling. But
Yeah.
But is it true for the languages on the right to left? Did they actually test it on
For Arabic?
Arabic
Or something like that? Well, so for Arabic, everything just goes in the opposite direction.
Right. I
It's,
mean, I guess my question is, did they actually test the directions per language? If the natural direction actually works better.
I don't know if people have extensively tested that on lots of languages. It might be interesting to see if it's more prominent for certain language families, for example, with more or less free word order or something like that. But, yeah.
Is there any way of recovering from the mistakes if you make a mistake early on while doing that communication?
So that's a good question. The way you normally recover from mistakes is by doing beam search, where you keep around several hypotheses at once. There are more tricky ways of doing search, but basically recovering from mistakes in a way can be viewed as a search problem. That being said, next time Max will be talking about CRF models that do dynamic programming to find the globally most consistent hypothesis, and those basically have a built-in recovery mechanism also. So there's a number of different ways, but for this particular model, beam search is the normal way. Yeah.
If let's say we have a sentence and we do this round of independent parsing, shallow parsing in which we don't really look at the structure, and then we observe that certain thing has a particular tag, it might be the case that starting from that position is a better idea than starting from left to right. So what I'm trying to say is that if we use the output of that classifier the way we would traverse the tree, that would probably be a better way of tagging than.
So for dependency parsing, for example, one somewhat successful technique has been easy first, which is basically you take the easiest decision and make that decision, and then you base all your other decisions based on that. What you described sounds like a different version of easy first that I don't know if anybody's tried before, so no. sounds interesting. Yeah. Okay, so I will move on to the next one, which is training structured models. So the simplest training method, this will be our baseline, and it's what we used in our encoder-decoder model before, is teacher forcing. So teacher forcing is just feed in the correct previous tag. So we already know the correct tag for the whole sequence. So we just feed in the previous tag when we calculate the representation that we'll use to make our decisions. So this is simple, and it's used in a lot of models. And we have a demonstration. Sorry, these file names are a little bit old because we changed the file structure, but we will be able to show an example of this. So, would you? Hang on one second.
So you teacher forcing on training time, right?
This is training time, yeah. So the slide says the slide was training models. Oh, so this is a demonstration of the bi-LSTM tagger in general, and then the teacher forcing, or the feeding in teacher forcing. Do you need something?
Well, I just want to.
Make it bigger.
Yeah.
Oh, you don't. Sorry, this is the video. So what you want is over here, on the screen.
Oh, okay.
That's confusing. Okay, there we go.
So first we talk about using basically no structured prediction model, just a bi-LSTM, and at each position you just predict labels independently. So we have training files, which this is NER tags. We use the BIO tagging as we shown before. So we have a training file and develop. Okay. As before, we set up by reading all these files. Well, here we build a bidirectional ion builder with this DINET. DINET has a bidirectional ion builder which can help you build a forward and a backward ion at one time. And then we have the softmax matrices which help us to predict each label. Normally we will have a lookup table only for word embeddings. Later we will have another lookup table also for the tags because we need to use tags as input. That's for teacher forcing. In this simple bi-LSTM model, we don't have that. So the prediction, as we can see in the cal score function, which is very simple, we just do a fine transformation. Basically, we multiply the output of the hidden layer to which is W, and we plus bias term, and then we just get that score, and we use that as a softmax prediction score to get each label. So I can't find the mouse. It's here. So here is almost the same training code we use all the time. At each place, we'll calculate the score based on the LSTM. So the transduce function actually gives you the whole hidden layer representations by taking a sequence. So by using transduce, when you put in the sequence in the LSTM, it produces, like, for example, if you have 10 words, it gives you back 10 hidden representation. So that means here we get this word representation, which are the hidden layer output by the bi-LSTM. And then, as we said before, we do this score using a fine transformation. We get that score, and from that score, when you pick the softmax, the largest softmax item, that's our prediction. So this is very simple. Every time we use a hidden layer, we multiply by a matrix W, we plus a B, we get a score, and then we pick the highest one as our final prediction. So you can see that each class, they don't really require anything before or after, so it's individual decisions. Do I also talk about teacher forcing right now?
Yeah, let me open.
So in this piece of code, we just modified the previous BioSTM with a lot of additions. Some of them we'll cover them later in the class. Let's look at the arguments. What are available here? So first one says there's a teacher forcing parameter. We have this cause and hinge, which we'll talk about later. So let's focus on how this teacher parameter changed the stuff. So whenever teacher forcing is activated, only a couple lines are changed, which are pretty trivial if you already have a BioSTM. So read the data as before. If we use teacher forcing, we now also have a tag lookup table because we have lookup tables are for embeddings as input to the system, right? For normal BioSTM, we only need word embedding as input. Right now, we also use tag. We concatenate the tag in the forward LSTM. That's why we need a lookup table for the tags as well. Here, we initialize the lookup table like randomly. We don't have word embeddings pre-trained or whatever because there are not many tags anyway. So another teacher forcing change is that we can't take the convenient BioSTM builder. We have to build the forward IN and backward IN separately. Because the forward one will have a teacher forcing component, we need to look at the previous tag. But you can't give the previous tag to a backward one, right? Because the backward one never, it scores from the right to left. It doesn't have the label information. So if we use teacher forcing, we will have the forward LSTM in a little bit different because the hidden layer has embedding size the input layer have embedding size and the tag embedding size. While when you don't use teacher forcing, you will only have like the embeddings, not the tag embeddings. Take a look at this. We have the hidden size output for the LSTM. In BioSTM, we actually because we have two of them, so we divide this by two. One for the forward, one for the backward. Now the backward one is actually simple. It's the same as the forward one, except that it doesn't have a tag embedding. The rest of them are almost the same, but during training we cannot use that. We cannot use the transduce method easily here, because we need to always fit the previous tag here. To do that, you have to like kind of manually iterate through the LSTM one by one. Here's how we do that. We take the LSTM's initial state, and then there's a function in Dynet which call add input. So each time when you add an input, it takes one of your input vector and compute LSTM gates and whatever to produce a new hidden representation. So the only difference here is that we are manually doing transduce instead of doing transduce using Dynet's automatic functions. One thing that we do is we use the previous output, right? We use the forward layer predicted output and then the backward representations together. So forward input is a concatenation of the word embedding and the tag embedding, which we look up the previous tag. So here, when doing training and testing is different. When we use the simplest teacher forcing, during training we are always using gold standard tags. And during testing, we're always using the system predicted test. So this function actually take a reference tag, which are gold standard. So when the function goes here, if we find some reference tag, it will put the reference tag as a previous tag. Here we have a sample function, which I'm not going to cover it right now. You can imagine this sample function always return true for teacher forcing. So when it's always return true, the previous tag will always be the reference tag. So that's the teacher forcing training training part. During testing, all you need to do is that you don't provide the reference tags. It will take the actual predictions in the previous test step. So I think that's all for teacher forcing, right?
Do we have to have a embedding layer for tag here, or?
We need to have embeddings for tags, yes, because they will be used as input to the system. You have to represent it in some way, just like the word embeddings. So I'm actually not very sure how large, when I implement this code, I'm actually not very sure how large the tag space should be. I just write 16. It looks reasonable to me.
16?
16, yeah. I mean, the 16-dimension vector, as opposed for the word embedding, we use 64. So it's a very empirical choice, I think.
Yeah.
Why can't we use transduce information?
So the transduce will take, well, during training, actually, you can do transduce. Because you know the tags already. But during testing, you don't, because you have to predict one by one. Here, the only reason is that I want to combine into one function. So I actually wrote 2 versions of that, but I think for demonstration purposes, it's easier this way.
So during the testing, the tag embedding doesn't matter anymore.
The tag embedding, well, you have to use the same tag embedding that you trained, right? When after you train it, you have to like keep the tag embedding dictionaries and doing the tagging. So here,
The hidden vector, I mean, dynamically generated.
Well, during training, you are kind of learning both the word embedding and learning the tag embeddings. That you are fine-tuning the tag embedding. Here, because tag embeddings are initialized randomly, the fine-tuning is all you learn. So it's actually very important to preserve that. And for testing, you are keeping the same set of tags.
So you input the embedding for the predicted tag at test time. At training time, you input the embedding for the actual tag. In teacher forcing. Yeah, very good. I have one more comment in response to this, which is that this is actually the better choice compared to writing 2 things for training and testing, simply because if you write 2 things for training and testing, it will break your code 95% of the time, and then you need to spend a lot of time debugging. So the closer you can write your training and testing code and reuse as much of it as possible, that's definitely a good thing to do. So I think this is better. That being said, it can be more efficient if you do it the other way, but unless this would still be pretty fast, and unless you really are having troubles with efficiency, the amount of time you'll spend not debugging will probably save the time that you would spend in running your experiments a little bit faster. Okay. So let me move back to the slides. So yeah.
In this model,
Mhm.
when the test time,
Uh-huh.
the model gives all the way to all the candidates for predicted tags, or just one most probable to predict.
Just the one most probable tag is the most common way. You could also think of taking a probability over all the tags and then mixing the tags together. People have tried doing this. This almost always works worse than just taking the one best tag. What's better is to do something like beam search, where you consider, the tags based on their score, and you can keep multiple hypotheses, and that will work better than just taking the one best. So, but mixing together the tag embeddings based on their probabilities is something that people have tried, but it usually doesn't work very well.
So the fundamental difference between add input of the dynamic interface and then transduces you care about these factors.
Transduce does a whole sequence at one time. Add input does a single input at one time. Transduce is a convenience function that does a for loop of add inputs. So if you don't want to write it yourself, you can use transduce. It doesn't make a huge difference. Okay, so I'll move on. So teacher forcing is very commonly used. It's actually used in a lot of things, and you probably, many of the people in this class can just use it without thinking about it too much. But if you want to get a little bit of extra accuracy, doing some sort of structured prediction is often a good idea. And the reason why is teacher forcing basically in these models has two problems. One of them is that teacher forcing assumes, when you're training using teacher forcing, you have your true output, and you're training using your true output. But at test time, you're using your predicted output. So there's a mismatch here, right? So as long as you predict okay, you're fine. You'll have a well-trained model. But the moment you make a mistake in your prediction, suddenly you get this wrong thing, you feed in this wrong thing, and your model has never seen any mistakes before, so it trusts that this previous prediction was absolutely correct. It has no doubt that this was correct. So what it will do is then it will go into this crazy state where it just trusts this and continues to do this forever. So this is a problem, and this is a very real problem. It's a bigger problem for models that are harder, like machine translation, for example. It's less of a problem for tagging, but it still is a problem. And this is called exposure bias. This has a name called exposure bias, and the reason why it's called exposure bias is the model has not been exposed to mistakes during training, which means it cannot deal with them at test time. It's been exposed to different data at training and test time. Another set of terms is local normalization versus global normalization. So local normalization, all the models I've talked about so far are locally normalized. And what this means is that every decision they make is a probability. So before every decision you do, you take a softmax and you calculate a probability, which means they sum to, they're between 0 and 1, and then you make that decision. This is, you can figure this out you can see that by taking the product here, and each of these sums to 1. In contrast, globally normalized models, which were called energy-based models in the reading, are models where each sentence has a score. This is not normalized over a particular decision, but it's normalized over the entire sentence, or the entire sequence of decisions you'll make. So it looks like this. All of the sentences or the sentence on top is your actual sentence. The sentence on the bottom is all of the sentences in your vocabulary, or all of the possible candidates that you're going to be looking at. And if you remember in structured prediction, what were our options? Our options were k to the L, k tags times to the exponent of L, or it's infinite in something like machine translation. So this is an extremely large sum. It's so large that we can't enumerate over it. In contrast, the sum at the top, this is over the vocabulary. This might be a big vocabulary, but we can enumerate over it. So the top one we can train using relatively simple methods. The bottom one is harder to train. However, locally normalized models have a problem called exposure bias. This is an example from a paper on CRFs, which we'll be talking about next time in detail. But basically, let's say we have two paths that we want to decide which path is good. And we have basically an RNN-based model that reads in all of the previous things we've seen and chooses which of these paths to take. And then we see R into R. These are exactly the same, so they'll get exactly the same probability. Then let's say we have Ri, and the model likes Ri. It's seen Ri a whole bunch of times, so it gives it a high score. Then we locally normalize over all of our choices, and we get a probability of 1. Because there's only one choice, so if there's only one choice, the probability of that choice has to be 1. On the other hand, the model really hates RO. It got a it's never seen RO before. This language doesn't ever use the word RO. But it gives it a score of -15. Then we take our softmax over a vector of size 1 with a score of -15. And suddenly the probability becomes 1 because we're dividing by this value. So still we get a probability of 1. And then maybe in B the same thing happened. Or in B the same thing will happen because there's only one choice. So the problem here, just to summarize, this is a really oversimplified example that I got from the CRF paper, but this is something that happens all the time. And basically, this is an instance of something called label bias, and it's basically the problem that locally normalized models can't penalize things that they realize were bad later. They can't penalize decisions that they realize were bad afterwards, because still they have to give a probability that sums up to 1 over the decisions that they're making. So because of this, in contrast, let's say we had a globally normalized model where the probability of where R, we have RIB, ROB, we have plus 0.5 for both of these. Then we have 2. Then we have -10. And then we have 1. And then we have -2 or something like this. Then we sum all of these up at the end. And we normalize. And because we summed and normalized, now the sum of these is 3.5. And the sum of these is -11.5. And this gets a much higher probability than the other one. So basically, by waiting until the end before we sum up our scores, we can penalize like all our choices in a particular state and give them all a large negative score. So the model can go back and say, oh, this was a really bad idea to pick this earlier on. So that there are advantages of using global. But there are problems training, so the denominator is too big. So we must do something tricky. One thing we can do is consider only a subset of the hypotheses, which we'll talk about this time and next time. Or we can design a model so we can efficiently enumerate all of the hypotheses, which is what we'll be talking about next time. Yeah.
What would be good loss functions which depend on the entire sequence but not just the pair of decisions?
What would be good loss functions that depend on the entire sequence, but not just, yeah. Well, I'll be talking about some of those. Yeah. Yeah.
Are all locally normalized models also globally normalized in the sense that they form valid distributions over
Yes. Yes. Yeah.
It's probably a simplification, but are locally normalized models, are they Bayesian networks, and globally normalized models, are they macro-dimensions? Is that the correspondence? Or are there exceptions?
That's a good question. It seems. Does anyone know graphical models well? I tend to think the answer is yes, but I don't want to say yes without being very confident about that. The question was, are all locally normalized?
But you can always
Yeah.
locally normalize
Yeah.
part of the Bayesian network or globally normalize
Yeah.
the whole network, right? So the difference between CRF and
Yeah.
Bayesian network is directionally, right? Not locally normalized or
Yeah. Well, this is a very good question, but unless somebody here can answer with confidence, or are you confident about that?
fairly confident.
Fairly confident. Okay.
I don't know.
Okay. Okay. Yeah. So I'll try to get back to that, but globally normalized models. Yeah, I'll get back to that just in interest of time, without working through it myself. Okay, so one very good way to train global models, not necessarily globally normalized models, but you can call them a global model at least, is the structured perceptron algorithm. And this is a very, very simple algorithm that people may have heard of before. But it's a very simple way to train non-probabilistic global models. So the reason why I'm not calling it a globally normalized model is because we don't explicitly calculate a probability. But it's very similar to a globally normalized model. And if you wanted to make it a globally normalized probability, you could by just summing up all the scores and dividing appropriately. But, okay, so the way we do this is we find the one best hypothesis, and if its score is better than the correct answer, we adjust the parameters to fix this. So if we write it out in an algorithm, it's basically 4 lines long. So in the first line, we find the one best according to the score. But we find the one best that is not equal to the, well, actually, in this case, we can find the one best or the one best that's not equal to the correct answer. Either is okay. But for consistency down the line, I'm saying we're finding the one best that is not equal to the correct answer. Then in the second one, if the score is better than or equal to the score of the correct answer, then we do a parameter update where we increase the score of the reference and we decrease the score of the one best. And here I'm giving an example of updating using stochastic gradient descent, where we add the derivatives and multiply it by alpha. But we could do this in any other update. If we wanted to use Atom to do this update, we could as well. So basically here, we are moving in the direction of the correct answer, and we're moving away from the direction of the incorrect answer. And we can express this as a loss function. So the way we do this is we basically take the max of 0 and the score difference between the one best and the other one. So you can see, basically the reason why we take the max is this max corresponds to this if statement. If this if statement is false, we do nothing. So our loss is 0, and if our loss is 0, we don't have any gradients, so we don't do anything. If the loss is not 0, then we basically have this here, and then we can take the derivative of this and do the update according to this. Yeah, the resulting gradient looks like the perceptron algorithm. Oh yeah, sorry, I actually had wrote this on the slide. So this is what it looks like. And the interesting thing here is this is a normal loss function. It can be used in any neural network that you would like. A lot of people have probably heard this, if you've heard of this, in the context of linear models, where basically you add the features that the linear model calculated and subtract it, add the features of the correct answer or subtract the features of the incorrect answer. But this is equivalent to doing whatever you heard you did in linear models, basically. But you can use it with neural networks as well. You can use it in DINET or whatever. But one major difference from the previous things that we talked about is that now this requires finding the argmax. It requires finding the highest scoring sentence in addition. So now we need to do prediction during training time. So this is very different from the models we've done before. The models we've done before, we didn't have to make any predictions at training time, but now in this model we do. So to contrast the perceptron with global normalization, if we think about a globally normalized probabilistic model, it looks like this, basically. Our loss might be the probability of the correct answer, which is normalized by all of the other things here. Whereas the structured perceptron loss looked like this. This is what I just introduced on the last slide. We could also think of something like the global structured perceptron. So the global structured perceptron would be basically where instead of taking the argmax, we just enumerated over all of the other hypotheses and took the sum of these loss functions. So there's kind of two differences that move us from the globally normalized model to the structured perceptron. One is that we're changing the loss function, and the other is that we're only taking the one best. So there's kind of two steps to move from the globally normalized model to the perceptron. Oh yeah, and the bottom one has the same computational problems as globally normalized probabilistic models. So one thing I should mention is that the global models, or one of the problems with this is that neural networks have lots of parameters and a big output space, which means that training is hard. And there are trade-offs between the training algorithms. So if we select just one negative example, like we do for the structured perceptron algorithm, training can become inefficient. And what I mean by this is, sorry, the slide's a little bit confusing, but what I mean by this is in contrast to things like locally normalized models, because locally normalized models, if you think about it, they're considering the whole vocabulary when they calculate the softmax, and gradients flow back through all of the elements in the vocabulary. So this one, if this one's the correct one, this one gets a plus, and then all of the others get minuses. In the structured perceptron, we only have a single negative example. So only this one gets a minus, and all of the others don't change at all. So this is kind of like negative sampling. Also, if you think about it, we talked about negative sampling earlier, and it shares the kind of same problems. Teacher forcing, on the other hand, efficiently updates all the parameters, but it has the problems of exposure bias and label bias. So which one do you take? And the answer in neural networks is very commonly, this is not the only answer that there is, but one of the things that people very commonly do is to pre-train with a teacher forcing type model and then fine tune with a more complicated algorithm. So you reread in your model and you tune with the better algorithm in the end to get the best performance. Yeah.
When we do global normalization in the contrasting perceptron, you know, the probability sy given x is changing as the single input goes by. So isn't it too expensive to compute the partition function?
Oh, so the structured perceptron, we never calculate the partition function. That's actually one of the advantages.
Okay. I see. But you know, but the probability s is changing, so maybe.
The score of S. So S is not a probability actually. S is just a score. It doesn't need to be normalized.
So, I have
Yeah.
a question.
Yeah.
Does the your predictor is an argmax, right? Is it always larger than the gold standard output? So there's no need to do a minimum between 0 and maximum. Yeah.
When you take the argmax, it's always better than larger.
Always larger. I mean, the
Well, it's always larger or the same. It could be the gold
yeah.
standard
So you
output.
don't really need that max over 0 and unless you have margin.
The only reason why I did that is because you need it for the margin later. Okay. So the question was, if you go on.
Just make it easier for you.
Yeah. So the question was, because the argmax is always guaranteed to be greater or equal to the gold standard, we actually don't need to take the max in the loss function because that loss function there will always be greater than 0, greater than or equal to 0. And that's true, but we need it for the thing I'm going to talk about next, which is why I used it in.
Can you explain the explanation which Golda has written in the book where he talks about essentially the probabilistic model and then margin model and then the distance model. And he talks about the criteria selecting the.
I'll do that later. I'll do that later. Yeah.
Okay, so I asked the question because in the implementation, I actually didn't do that max between 0 and that score. So just to, so I asked the question to clarify. Otherwise, you think I'm implementing wrong. I'm not. So let's look at another argument here, just adding this perceptron. So in the previous demo, we didn't show that, one thing we didn't show that is the loss. But here, the only thing changed is the loss. So when calculating the loss, it's actually at the training part, I think. So we calculate, we call a function calcloss. Let's find calcloss. When using structured perceptron, we are calling a different function. When not using, we're just using MLE. Basically, to see how the scores and to compare the score and text. With structured perceptron, we have to do perceptron loss. So let's look at how perceptron loss is implemented. Let's ignore this cost augmented thing first. Let's assume this is always false for now. When it's false, one thing we are doing here is that we are doing a prediction. That's what we do that's what Graham talked about. We have to do one prediction during the training, right? So we do the prediction. For each score, we just argmax to find the best index we have. So this prediction is actually pretty trivial. We pick the high score index for each position. So we get a prediction. And then let's ignore the margin for now. After getting the prediction, we calculated the reference score and prediction score by a function called calculated sequence score. Let's ignore how we calculate this for now. But we know that prediction score is the argmax. It must be larger than the reference score, right? So when we do prediction score minus reference score, it's always larger than 0. So we don't need to take the max between that. When we want to add the margin and other things, we probably need that, but that's for the next demo. So ignoring all other conditions, the loss is just prediction score minus reference score. And that's actually pretty trivial to compute, and we return this loss instead of the MLE loss. For how to calculate the sequence score, it's actually just summing up for this case. We're just summing up each position, taking the tag, and we just sum up the tag score for the whole sequence. We'll have more complicated way of calculating the sequence score in the next lecture, I think. But in this case, we are making single decisions each time. So all looks pretty simple. So that's all we have changed to make perceptron loss work. We need one function to calculate sequence score, and we need one prediction during the training. I think that's it.
And for the perceptron loss, these scores were calculated by searching, right?
Well, doing prediction, right? So prediction is a way of searching.
Yeah. So you searched for you searched for the correct answer to get these scores, right? Or you searched for the answer to get these scores.
This is we search for the answer. Search for answer will give a prediction. And this is the argmax prediction because we are we are making individual decisions. Right. You don't need to care about the structure much.
Yeah. I think that's right. I'll check, but basically this is I believe this is an implementation of the so that was basically an implementation of the thing here, like this. Okay, so I will move on. We're a little bit short on time, so I'll do this. I might actually not do the last part this time, and we can move it to next time maybe. Because I think this is important to cover carefully and understand well. But so the next thing is hinge loss and cost-sensitive training. So the basic idea is, I think almost everybody in this class will have seen something like this in a entry-level machine learning course. But which of these lines is better, the dotted line or the dashed line, if we want to separate these things? So who thinks the dotted line? Who thinks the dashed line? Okay. If anybody raised the hand for the dotted line, I'm reporting you to your machine learning instructor. But both of these have 0 perceptron loss. So so what we do, as you probably know from some sort of machine learning course, is we add a margin, and we can do this with something called the hinge loss. So the perceptron loss basically looks like this. It's the difference between the scores where the x-axis is basically, it will be larger the more the incorrect answer is worse than the, or is better than the, is higher than the correct answer. And then we have a margin, a hinge loss. So basically what the hinge loss is if we have a margin of 1, we start paying a loss, even if it's a little bit better, even if the proposed one is a little bit better, and or sorry, even if the correct one is a little bit better than the next best hypothesis. And the way we do this is simply by taking the perceptron loss and adding a margin term here. So we add m. And in this case, in the case of this graph, the m is equal to 1. And one thing that you should keep in mind about hinge loss is we can actually swap this in anytime we were using cross entropy previously. So like, let's say we did a cross entropy based probabilistic loss for our tagger. What we could do is we could just take a hinge loss instead, like this. And in DINET, it's as simple as doing something like this. We just take all our pick neg log softmaxes, we do a global search and replace, and we replace it with the hinge loss function. And we can set the margin to be 1 or whatever we want it to be set to. What would you want to do this? In many cases, the answer is yes. Sometimes this works better. In many cases, the answer is no. I don't think there's really any consensus, and people tend to like probabilities. So people often will take the first one, but the second one works pretty well for a lot of prediction problems as well. Another very useful thing, this was in the reading materials as well, is you can actually decide a cost for each mistake you make. So sometimes some decisions are worse than others. So if you take your verb and you mistake it into a VBP, I actually didn't know the difference between these two part of speech tags until I looked them up a few days ago. So the verb VB is the base form of the verb, and VBP is the non-third person present form, which is almost always the same in English. And if you make this mistake, it will, it will not have a big effect downstream. Your parser will still work most of the time, etc. However, if you mistake a verb into a noun, that's probably a pretty bad thing, because that will break everything. So the cost augmented hinge basically defines a cost for each incorrect decision and sets the margin equal to the cost. So each decision y hat has the cost y, or has a cost with respect to the correct answer, and you add this in place of a fixed margin, which allows you to basically say, I want to be much safer if I'm going to make a very bad decision. You can also do costs over sequences. So up until now, I was saying over a single part of speech tag, but let's say we have lots of part of speech tags in a sequence. One way to do this is a 0-1 loss. So if we make a mistake, we get a loss of 1. If we don't make a mistake anywhere in the sequence, we get a loss of 0. And this is basically what maximum likelihood models are attempting to optimize. They're attempting to try to make you not make a mistake anywhere in the sequence. And specifically, you can say they're calculating the risk with respect to 0-1 loss, I believe, which is the expected 0-1 loss. So yeah, that's what it looks like in equations. We can also think of the Hamming loss. So the Hamming loss is every time we make a mistake, we pay a loss of 1. So now our loss is just the sum of all of the mistakes that we make in the sequence. So this is better because let's say we have a part of speech tagger. We would rather have it not make 3 part of speech, 3 mistakes instead of making 1 mistake. So you get a bigger cost when you make 3 mistakes than when you get 1. There are other losses like edit distance, 1 minus blue score, whatever, if you're doing another task where you get evaluated on these. And you can use any of these if you like.
So when you do edit distance, you do something like cost augmented, like you have cost augmented.
With
it's like BP and then it's so different. Is there like in the Hamming loss, you don't have to use delta function and use this function.
Oh, for the Hamming loss, yes, we could replace this delta function with a part of speech sensitive cost function if we wanted to as well. Yeah, we could do that. Okay, yeah.
So are these used in the Hinge loss as weights?
In the weights?
So does the Hinge loss change based on?
You can do a Hinge loss over sequences, which I'm going to talk about next. Yeah. So structured Hinge loss, that's exactly what I was about to talk about. So it's basically the Hinge loss over the sequence with the largest margin violation. So we can think of, normally before when I was talking about the structured perceptron, basically what we did was we took the argmax and we found the sequence with the highest score and we used that as basically our negative sample. But in this case, instead of taking the one with the highest score, we take the one with the highest score plus the cost of the sequence. So what this says is you're making it really easy to pick something that's really bad if it has a high score. So anything that's really bad, we want it to have a really low score, so we don't pick it according to this. And this was the thing in the book that somebody asked about on Piazza. What it said in the book, I think, was we want to pick something that has a high score and bad, or high score and like relatively bad, or something like that. It was a kind of it was a very tricky sentence, but this is what the book was talking about there. It's exactly this function. And then our Hinge loss is basically equal to this, and the nice thing about this is by doing that search over the argmax of the cost plus the S, we will find the hypothesis that gives us the worst Hinge loss. And this is, out of all the hypotheses that we could choose, by taking the argmax with this particular equation, we'll get the worst Hinge loss. Another way we could do this is, like I mentioned before, we could do a global thing where we added over all of the possible sequences, but that's not possible for efficiency reasons. So this one gives us at least the worst Hinge loss. And in the original paper that proposed this is a paper by Ben Tasker et al. What they did a far more tricky thing, which was basically every time you found one of these, you added it to the set of the hypotheses you considered and then did some tricky batch optimization to try to get things to work. But basically, we could also use something like this in a stochastic gradient descent type algorithm where we just do this for every training example over and over and over again. And we can do a pretty good job as well. So how do we do the argmax above? How do we find this argmax? we kind of know how to find the argmax for S. We can do it with greedy search or we can do it with beam search. But the solution, but it's not entirely trivial when we calculate this cost, but in some cases, we're able to consider this cost when we search for the best hypothesis. And Hamming loss is one of those very lucky cases. So the way we do search, or the reason why is because Hamming loss is decomposable over each word. So the solution is we basically add a score equal to the cost to each incorrect choice during search. So we take our input here and predict scores. And normally here the correct answer is PRP. So normally we just select PRP and then we'd continue on with our search through the sequence. But instead what we do is we add a bonus to everything except the correct answer. And by giving a bonus to everything except the correct answer, now 0.5 plus 1 for noun will now become the one that gets selected. So what we're doing is we're making it really, really hard for our model to find the correct answer, and then we're penalizing it every time it makes a mistake. So it's like a really mean teacher that gives you quizzes that are almost impossible to answer, and then hits you every time you make a mistake. So if you don't feel sorry for your neural networks, you can use this cost augmented decoding. And then, of course, if you make a mistake, you feed this back in. So the worst thing about this is now you feed it back in your mistake, you're more confused, and you make more mistakes until you get the whole sequence wrong. But every time you get the whole sequence wrong, you learn to do it a little bit better. And so this is actually a very nice training algorithm. So yeah, let's try this.
So the main thing we need to do here is just we added cost, we added Hinge, add this 2 argument to this function, to this script. We're always talking about search, but currently our model is only doing local decisions. So search is basically finding the arguments at each position. Let's just take a look at how the mean teacher work. How the mean teacher work. So this is this function is called Hamming augmented decoding. So we add Hamming loss into every during decoding we add a Hamming cost to every incorrect answer. So we have to know the correct tag for this case. We take the scores and we know the reference tags, and for each time the current scores are actually predicted by the system. And the cost we computed whether, so the cost for, if it is incorrect, the cost for this reference, the only index that doesn't, the only tag that doesn't get a cost is the correct one. So cost for this is 0, the other ones are all initialized as 1. So this is a Hamming loss, it's either 1 or 0. And then we just make the augmented result as by adding the original scores and the cost. Because the correct one now is 0, you don't add a cost for that. For the rest of them, you all add a 1. So here, that's how you get the augmented score. So this is the original score, and we return the augmented scores for every case. And after doing this, the rest of the function doesn't get changed. Where did I call that? It's hard for me to find where you call that function, but basically it's too long. But basically, it's whenever when you want to use the augmented scores during a prediction, when you do an argmax, you just return that and use this as a search result instead of the original one.
Just to confirm, this is on training time, right?
This is on training time. I mean, look at this. You have a reference gold standard here. At testing time, you don't get that. Otherwise, just return that. Right. So I think that's all for Hamming augmented decoding. But to add it to the loss function is also not very. It's also very straightforward. Let me find the loss function.
Why does speeding the fuse now up, like round up?
It reduces exposure bias. So it basically, you're helping your model get out of very bad situations.
Yeah.
Okay, I find it here. So if you use cost augmented, the final thing is you get the loss is the same. You're just using the prediction score to minus the reference score, where the prediction is decoded using Hamming augmented decoding, right? So so you are likely to get wrong decisions by adding the cost in this prediction, and then the prediction score. So one thing to note that is the prediction score is not, if you do this calculate sequence score on the prediction sequence, you don't get the actual full Hamming stuff. So you have to add it back here and then minus the reference score. Well, it might seem a little bit tricky here, but all you need to remember is just you have to boost the incorrect ones, and then also add that boost during the loss. Otherwise, the prediction score is possibly to be smaller than the reference score. That's not what you want. You remember to add the boost here, and then if you use Hinge, you just compare whether 0 is better when you do that. So here I have another different margin, which is not the margin that Graham talked about in this lecture. So Graham says use the cost as margin. You can also supply another consistent margin for every decision, which is not covered here. So I think that's probably not that important, but the idea is the same. You want to add a large margin between the correct and the incorrect ones.
Thanks a lot. So as promised, I will skip the last part of today and move it to the next time because I don't want, because we have 1 minute left in the class and I don't want to keep people. So is there any last question or yeah?
Is the constant margin chosen by cross-validation?
Is the what?
Is the constant margin
Chosen by cross-validation? You can do that, or you could just choose one. There's not a really strong motivation for having a big margin or a small margin. It's unlike the margin in traditional support vector machines where that actually had kind of an effect of regularization. If you've used a traditional support vector machine toolkit, the strength of the soft margin thing had a big effect. Here, that's not the case. It just needs to be, a reasonable size. Of course, if it's 10 million or 0, then that's not good. But 1 is probably reasonable, or 1 times the cost anyway. Yeah.
I know that the reinforcement learning can also help reduce the exposure bias. So which one do you use?
I think either is fine. I'm going to talk about reinforcement learning later. We're also probably going to talk about minimum risk training. Reinforcement learning, there's a lot of reinforcement learning algorithms also with very different characteristics. So it's kind of hard to say reinforcement learning is a single algorithm. But
just for the structure.
Yeah, it's I don't know if anybody's actually looked at that very closely. My impression is that margin-based methods are actually very good. They work well. They're flexible. But it's in the end, it's an empirical thing.
There's also LCM CRF.
Yep. And That's next class.
Okay.
Yeah. Okay. Thanks a lot, everybody.
The question I had about